turn down this microphone because Anya is much taller than me. And at least this one works. I think the other two are kind of not charged yet. The light's flashing red, which is not a good sign. So it will be a bit less walking around.
There we go.
So today we have another one of these overview lectures. So yesterday I was an entertaining act between Brigitte and Brigitte, and today I'm an entertaining act between Anya and Anya. So let's take it as it goes. And today I want to talk to you about modal logic and also a little bit about linear logic. And I kind of decided, kind of following the style of yesterday, I started kind of with an old quote from Bertrand Russell. This one is before his paradox thing, it's 1905. And as you can see, and you can read in the slides, he thinks that the whole idea of modality is kind of bullshit. They shouldn't kind of pay any attention to that. But, so he says that there's no one fundamental logical notion of necessity, nor consequently of possibility. And if this conclusion is valid, the subject of modality ought to be banished from logic, since propositions are simply true or false. So it is an indictment, right? We are up against something. I mean, the man was not stupid, to say the least. But we are not going to agree with him in either of these two things that he's saying. We're not going to agree with him that modality is not important, and we're not going to agree with him that knowing something about necessity kind of consequently means that you know it about possibility. So let's see how it goes. Previous versions of this this talk had some Google books and Google search showing numbers about modal logic, because one of the things that one can say is that modal logic is one of the most successful uses of logic in computer science. And we much prefer this quote from Professor Dana Scott, who is also in the Topos Institute, who said in 1972, and he objects to the fact that I'm using a picture of him from more recent times, but in 1972, he said that one often hears that modal logic is pointless because it can be translated, blah, 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 blah. But there is no weight to the claim that the original system must therefore be replaced by the new one. What is essential is to single out important concepts and to investigate their properties. And that's a theme that's been running through the lectures so far, right? I talked a lot about structure, Brigitte talked a lot about structure, Anya talked a lot about structure. We all kind of think that important concepts have to be investigated, and the properties are what we want to think about. So, as I was saying, modal logic is one of the important bits of logic in computing, and as I was saying here, most successful logical framework in CS. And the basic idea is fairly reasonable, right? Is that box A means A is necessarily the case, A holds for all times, there's lots of different interpretations using words, but we kind of, some of us at least, tend to think about the logical inference rules as explaining what box A is, and the closest to my mind is this one, that something that is necessarily the case. And diamond A is possibly the case, and A holds at some time, and stuff like that. And we have temporal logics, knowledge operators, so you think of box A as A is known to be true or known to agent A, or to agent, whatever, agent Bob to be true. there's this belief, BTIs, models, belief, whatever, I can't remember what this, the acronym stands for. Thank you. There is the notational semantics, effects, security modeling, as we saw in Lenin presentation yesterday, databases, lots of things that have to do with logic representation of information and reasoning about it. But mostly, until kind of 20 years ago, people only talked about classical modalities. And this is a slide that I stole from Frank Fenning, saying that, you know, the Turing Award of 1977, the ACM Canalax Award of 1999, and the whole of the semantic web are uses of classical modalities. But we want to think about constructive reasoning, and that's something that I touched on yesterday, and I don't know if you noticed, but both Brigitte and Anya kind of took for granted that we want to do constructive reasoning and not classical reasoning most of the time. And so it's kind of worth stopping a second to discuss why this is the case. And I think there are several reasons why people might want to do think about constructive reasoning, particularly in computing, but even in mathematics itself. Because if you ask whether there is an X such that P of X holds, personally, and I think most of you will be much happier if I can say, yes, and that's the X. P of this X0 here, it holds. Then, if I kind of try to use a circumlocution like yes, for all X is not the case that not P of X. You know, we'll do that if need be, but it's not so nice. It's much nicer to be able to exhibit, to have a witness of whatever you're saying is the case. So, we want our reasoning to be as precise and safe as possible. As Anya was kind of showing up with particular examples today, right, of the I think her example of the LASIK surgery kind of struck a chord with lots of people, that, you know, you do want to know exactly where things are going. And the fact is that constructive reasoning is better whenever possible. And so we want to, at least for the purpose of this lecture, we want to be as constructive as possible, and classical if need be, because classical will tell us if things are kind of true or false, or at least give us a very good indication of which direction we should go for. So today we're talking only about constructive modalities. And I think I vaguely hinted at that yesterday too, that whenever you try to constructivize some sort of phenomenon, the possibilities multiply themselves. So there are some things that we take for granted, like, you know, if we're going to think about constructive modalities, or we want to think about these modalities over an intuitionistic, and in my case, propositional basis, but of course, we have an eye on the future that we also want to do it for kind of dependent types and stuff like that. But, you know, we start simple, so we start with the propositional basis, and so we need to have connectives like conjunctions, disjunctions, implications, and negations. So we know that the basis is that, and then we want to put modalities on top of this basis, and that's the name of the game. Which modalities, which constructive modalities can we put on top of this constructive basis? And we also have some worries kind of from the back of our minds, like, I don't know how much you guys looked at that, but there's an awful lot of modal logics. They are many systems. And we might wonder with Professor Russell, if that quantity of modal logics is a bad sign, if it means that they are not really necessary because there are so many of them. And even if we don't take this view, we might say, well, how do I choose my best constructive modality, my best constructive modal logic? And we definitely want to think very hard about how they relate to each other, right? We want to be able to tell which properties of which modal logic are preserved in other modal logics and which properties are specific to certain systems. And we want to have kind of the usual theorems that we have for intuitionistic propositional logic and intuitionistic first-order logic and intuitionistic higher-order logics and type theories if we can. So, in particular, and I know some of you here, or at least one of you here, is very interested in the useful applications of these constructive modal logics. But before I go there, I wanted to mention this business that, constructive logic in general has given us all those notions of type theories and of kind of different type systems that are useful for several different things in computing. So constructive logic is useful for computing. Modal logics are very useful for computing, like I just mentioned, all these awards and all these systems, these engineering systems that are kind of built on top of modal logic. So presumably, constructive modal logic should be twice as useful, right? Because you should be able to use all the good things that we have for constructive logic and all the good things that we have for modal logic. So why there's so little work on that? And that's one of the main reasons for giving this lecture is actually discussing what are the issues, what are the problems with that. And of course, one first reason for not being twice as useful might be because we haven't kind of got the right version. We know that constructivization is hard. There are lots of possibilities. So maybe we haven't got yet to the right one. And it's a possibility, and we should discuss it. So, as I was saying, I don't know how much you guys pay attention to the difference between constructive logic and classical logic, which most people think of normal logic. But one of the main differences, as I was explaining a minute ago, is the existence of witnesses. Is the fact that you have to be able to exhibit the witness for a proposition. And another main characteristic is this business of not having an interdefinability between for all and exists, the same way as I mentioned before. So you expect for the modalities, and the modalities look very much like quantifiers. They look like easy quantifiers, right? Because modal logic is decidable, which is one of the reasons why we like them so much. So you expect that you don't have interdefinability between box and diamond. So that's my first item here. We expect that, and we want that. But you don't want them to be completely separate, right? You don't want them to not have anything to do with each other, because they do, right? The meaning of necessity is related to the meaning of possibility. So you actually have to look at the expected behavior and the tools that we have and try to extract the best system that you can. And kind of since 1984, people have already said, well, that should be a a very developed field, but it isn't. So this is one of the first handbooks of logic, the Handbook of Philosophical Logic in 1884 already said this business. Well, we should have constructive modal logics, but we don't. And that's because the proof theory of modal logic is difficult. I've forgotten something that I was going to say just after Russell's thing about not having modalities, which is that the first handbook that I know of logic, the one from 1977, edited by John Bowise, it's a handbook of logic in general, and it has no modal logic whatsoever. You go to the index and you check modal logic and there's nothing. And you look at the subjects there, and mathematicians did follow for a long time Russell more than Dana Scott. I mean, if you are very well up on it, you can realize that there is something in the handbook on crypt-joyal semantics. And then you realize that, yeah, there was some modal logic, but it was totally implicit because people were following this theory that maybe modal logic is a little bit iffy and kind of strange. Now, since kind of 84, and since people started paying attention to this problem of finding good systems of constructive modal logics, lots of people have gone into the game, and there's an awful lot of things that you can add to the syntax. So, as I mentioned yesterday, and as Brigitte mentioned yesterday, there's both main systems of logic that we use nowadays, both sequent calculus and natural deduction, and also natural deduction Martin-Liv style. All of these systems have a very simple syntax. They are very direct. I grew up earlier that some of the logic rules that you put up are very scary. You look at that and there's too many symbols. You have to kind of keep your head straight on what is that important in each bit of the rule. But still, they are kind of, they tend to be, and you've heard this expression before more than once, they tend to be local. The syntax is, the soundness is local, the completeness is local, we try to keep things local. And one of the problems with modal logic is that this is much harder to do for modal logic. They become much more about global notions of validity. So people do add to the syntax. So there's things like hypersequence, there's label deduction systems, nested sequence, tree sequence. All of them add some extra syntax, some extra bit that are trying to cope with the semantics to the syntax. And I'm going to try to show you some of it and some of why this is the case. But yeah, kind of, as yesterday, this is about kind of stories. And one of the stories that I want to mention to you is that there's been a collection of meetings called Intuitionistic Modal Logic and Applications. I have to make a little bit of self-correction. Most of the time, I will use constructive and intuitionistic to mean the same thing. They are not exactly the same thing, and I tend to think of constructive as being more general than intuitionistic. But in certain cases, some people have used the opposite convention, so makes life a little bit harder for everyone. But be aware that there is this small issue. So, as I was saying, there is this collection of meetings called Intuitionistic Modal Logic and Applications, and this is, as I'm saying here, is a loose association of researchers and meetings and a certain amount of mathematical common ground. And basically, IMLA stems from the hope that philosophers, mathematical logicians, and computer scientists would share information and tools about these kinds of constructive modalities if they knew what the other guys were doing. I have this information that this effort to kind of putting people together in the same room and making them pay attention to the other people's work has not been extremely successful. I think there's still an awful lot of things that happen only on the realm of type theory, or only on the realm of kind of logics as logics, not thinking of them as being related to a type theory, than I would like to have. I think, there's quite a bit of work to be done on this bridging between communities. But we've been trying. So these are the meetings that we had. So it started a long time ago, in Flock, 1999. And the last one that has happened was in ESLI 2017. And ESLI, if you guys don't know about it, it's the European Summer School on Language, Logic and Computation, which is a bit similar to OPLSS, but much more directed to linguistics and more kind of philosophical logic than what we have here. And there are lots of publications coming from these meetings, and I kind of mentioned some here. But I really feel that things have not been as well shared as one would hope. So, what is the state of play? I think Imla's goal was to get functional programmers talking to philosophical logicians and vice versa. As I said, not attained quite yet. The communities are still largely talking past each other. And incremental work on intuitionistic model logics continues. But within certain big research programs, and these are very unrelated somehow. And part of the business of talking to you about that is, is to ask you guys whether you think it makes sense to change this sort of situation or not. So, what did I expect when I started doing this kind of work 20 years ago? I expected that by now, 99 to 25, so we are 26 years later, I expected us to have fully worked out Curry Howard for a collection of intuitionistic or constructive model logics. I expected to have a fully worked out design space for how those constructive model logics related to the classical model logics and how intuitionistic logic could be connected to classical logic in general. I expected a full range of applications of model type systems. I expected fully worked out dualities between desirable systems, and also expected collections of implementations for both proof search and proof normalization in all this space of logics. And I thought it was going to be that easy. I thought it was going to be a walk in the park, because we had some very early successes. Systems like CS4, which I'm going to define in 2 or 3 slides, Lax Logic, CK, they had easy, they were kind of easy adaptations of the systems that we had for intuitionistic logic. And they showed Curry Howard the way I wanted it to be, in the sense that you could start from the type theory and forget the terms and get a logic, or start from the logic, add terms if you are clever enough, and get a type theory that had all the properties that we've been discussing this morning, for instance. All the properties of substitution, alpha conversion, beta conversion, subject reduction, all the stuff that both Brigitte and Anya have been talking about. And there's a problem with that. It doesn't work as well as I had hoped. And that's kind of what I wanted to, and the reason it doesn't work as well as I had hoped is very easy to see with hindsight. So I wanted to show you how you can see the issue. So one can start from what I call constructive CS4. And you might say, why? Start from 4? Why are you counting from 4? What is that? But CS4 is a system that was used by Gödel in the 30s again, and also to show that intuitionistic logic is embedded in classical logic, in terms using provability notions, and was used also by Girard, who when he came up with linear logic, showed that some of the rules that Anya is taking for absolutely granted, and most of us take for absolutely granted, like the weakening rule, this rule that if I can prove an A by using some hypothesis that I call gamma, then I can add a hypothesis that I'm not going to use, and I still have a proof. So the weakening rule, as Anya went over quite carefully this morning, maybe it's not a rule that we want all the time. It is a rule that we want in classical logic. It is a rule that we want in intuitionistic logic, because we are thinking of them, of the main objects of investigation there as propositions. But if you're thinking of the main objects of investigation as some sort of resources of your system, thinking of the formulas of your system as resources that you're going to consume and use or produce, then maybe that rule is not such a good idea. And that was Girard's main motivation for introducing linear logic. But of course, he did not want just to introduce a weak system that couldn't do much, that, if you have an A implies B, and you have an A, then you have a B, but you lost both your A and your A implies B because they've been used up. He wanted to have his cake and eat it. So he wanted to have the ability to think linearly in certain cases, but also think normally, meaning classically, or constructively, whenever that was more suitable. And he came up with this bang operator, which satisfies the rules for the box operator. And I'm now giving you the modal axioms. And I normally don't like to think about modal axioms. I much prefer to have the rules in sequent calculus or in natural deduction, as we discussed yesterday. But modal axioms are easy to understand, and they have their utilities. So they're very good when you want to prove properties of the whole system that you're dealing with. They are not very good when you want to prove theorems, prove results for yourself, or things that you are interested in. But to show properties of the whole system, they are good. And the box theorems, which are the same, the box axioms, which are the same as the bang axioms, have this sort of shape here. If something is necessarily true, let's see if I can make this work or not. When Anya was using it, I couldn't see it, and I still can't see it. So I'm going to point using this thing. So one of the things that we say is that if something is necessarily true, then it's true, and if something is necessarily true, then it's necessarily true, and if some implication is necessarily true and the hypothesis is necessarily true, then the consequence is necessarily true. So you see that I'm actually reading it courage instead of the way I've written it here, but it's the same, right? One of the main things for me and for lots of people is this idea that you can curry and uncurry implications. So these first axioms here are perfectly reasonable for both necessity of truth, right? Something being necessarily true, and also very reasonable for linear logic, because they actually kind of are talking about necessarily reusable formulas. But the difficult, as I was kind of hinting about yesterday, is what to do with the diamonds. And clearly, if diamond is a possibility, if something is true, you want it to be possible true. It's already true, and it needs to be possibly true as well. But other rules are more difficult. So this system, S4, we start from 4 because of that, because the system is being used since the 50s. So since the 50s, we had these 2 sets of rules for box and diamond. And if you look at them, I mean, they're much smaller than any system rules, so you can pay attention to each one of them, right? So the first one says that if you have a gamma and an A, and you prove a B, so you are assuming your A, then you might as well have assumed a possible A, because the top implication is an hypothetical in any case. The second one is the complicated one. It's called, in linear logic, promotion. Because what it says, and that's the non-locality of the rule, it says that if A is proved only from hypotheses that are necessarily true, then and only then I can add a necessary to the A. So pay attention to that one, because that is the dark horse in this whole story. And the diamond rules they depend basically on the box ones, because on the necessary ones, the box ones, because you can only the way we manage to prove the theorems, prove the axioms that I was showing a minute ago, is using the idea that I had, that if something is already true, then it's possibly true just without any effort. But the similar one about adding possibility to the left is only on the context of having everything else boxed. And one of the things that I was saying is that we actually